Here's a solution to 15.204. We have a rod AB of length 13 inches connected by ball and socket joints to collars A and B, which slide along the two rods shown. Knowing that collar B moves toward point D at a constant speed of 36 inches per second, wants us to determine the velocity of collar A when B is equal to 4 inches. So I'm going to let the length of the rod here, L, be 13 inches. The velocity of B is at 36 inches per second in negative K direction. Lowercase b is 4 inches. R is going to be designated here the 7.8 inches. And C, this distance right here, is going to be 9.6 inches. And that comes from L squared equal R squared plus C squared plus B squared. So the velocity of B is going to be expressed as the velocity of A plus the velocity of B with respect to A. The velocity of A is in the J direction, and the velocity of B with respect to A is omega crossed into R sub B slash A. So V sub B then can be expressed as V sub AJ, and the omega crossed R sub B slash A is shown here in a matrix form with your IJK unit vectors, omega X, omega Y, omega Z, and then your R sub B slash A is R in the X direction minus C in the J and plus B in the K. So there's those terms. When you expand this, go ahead and express V sub B as V sub B times K unit vector, remembering that the value you put in for V sub B right here is a minus 36 inches per second. V sub A is unknown in the J direction. And then the I coefficient comes from B times omega Y minus C times omega Z, which gives you a plus C times omega Z. The J comes from R times omega Z minus B times omega X. And the K comes from minus C times omega X minus R times omega Y. So there it is. So if you look at the I parts of this equation, there's no I there. There's no I here, right there, but there is an I term right here, which would be omega Y plus C omega Z. The J term, none here. There's a J term right there, and then there's this further J term, R omega Z minus B omega X, and then the K term, there is a V sub B right here on this side, and then the K term is minus C omega X minus R omega Y. If you call these equations 1, 2, and 3, if you multiply equation 1 by R, you get this expression. If you multiply equation 2 by minus C, you get this expression here. And if you multiply equation 3 by B, you get this expression. Now, the way you know how to multiply these, you just kind of have to look to see. You're trying to get rid of omegas so you can get the V sub A. You have 4 unknowns in these equations. You only have 3 equations, so you can't solve for all of them, but you can solve for some. And so when you do this particular conversion right here, you'll notice that all your omega terms, when you add all 3 of these equations together, they all disappear. And so what you end up with is a BV B on this side and a minus CVA right there. And when you solve for V sub A out of here, you get 15 inches per second in a J. A rather unique way of looking at this problem is to look at this particular expression right here and note that if you dotted R sub B slash A, which you know, into both sides of this expression, then you would have R sub B slash A dotted into V sub B equal to R sub B slash A dotted into V sub A, and R sub B slash A dotted into this term is going to be 0 because omega crossed into R sub B slash A gives you a vector that is perpendicular to both omega and R sub B slash A. So if you dot R sub B slash A into a vector that's perpendicular to it, you're going to get 0. And so when you put in R sub B slash A as Ri minus Cj plus Bk, you dot it into V sub Bk, and do the same thing on the right-hand side, dot it into V sub A, and what you're going to pull out is B times V sub B right there, and you're going to pull out a C times V sub A right there, and if you'll notice, that's the same expression we had a while ago that yielded 15 inches per second in the J direction for V sub A.